Okay, welcome back from break, everyone. I hope it was nice discussions and you're fully re-energized for our first panel of 2 of the day. This one is going to be about data science at the energy-water nexus. It's going to be moderated by Professor Jason Wren. Let me give a brief introduction to Jason. He, like me, is an associate director in the Andlinger Center. He's the associate director for research at the Andlinger Center and also a professor of civil and environmental engineering. He's relatively new to Princeton. He only joins us for the last year or so. And he's an expert in environmental bioengineering with expertise in energy harvesting from wastewater and broad research interests in areas linked to the water energy nexus. So I'll invite Jason up now to set the stage and introduce his panelists for today.
Thanks so much, Farid. Good morning, everybody. It's really my great pleasure to moderate this panel. Before I introduce our distinguished panelists, I want to say it was great keynote and discussions. And in that session, we talk about environmental stewardship, and we talk about resilience. And if you think actually all these climate-related events in recent years, everything mostly actually related with water, right? Either we have too much water, talk about floods or hurricanes, or we have too little water, talk about fire. And on the other side, I want to note like the water, wastewater industry itself, the utilities, are among the biggest energy consumers in the nation. So with that actually nexus between water and energy, we assembled this panel to really to understand how do we use actually state-of-the-art tools, for example, data science, to transform water industry as well as affiliate with energy topics. For example, how would you really mimic, say, the smart transportation? Some of you probably took Uber or Lyft, came here, right? And the smart grid system where we would be able to use data science to optimize the grid to incorporate renewable energy, solar and wind, into the grid. Very similar approaches can be used in water, but this industry is very conservative in a way, and well, public utilities are very cautious on things, but we have transformed energy industry, so water is actually another very critical infrastructure we really think we can revolutionize using some of the modern approaches. So with that, so we really have several leaders actually in this field. They've done a lot of pioneering work, because this is a really very new area. We just start to explore this area, so I want to introduce them. I'll start with the gentleman next to me. Jeff Moeller is a research unit leader, and he actually directs a major research program at the Water Research Foundation, just south of DC, Alexandria, Virginia. And we worked together quite closely in the past few years in developing a national testbed network for water resource recovery and energy recovery. So it's a national steering committee. So Jeff's going to talk about some of that, and also WRF initiative on data science and water and energy. And next to Jeff is Professor Qilin Li. So Professor Li is a professor at Civil Environmental Engineering at Rice University. She's also the co-director of a major national science foundation center by using nanotechnology for water energy applications. Next to Qilin is Saman Farid. So Saman is a venture capitalist. So he has been pioneering on actually several funding programs in funding startup companies into actually waste management field and water smart sensing programs. And next to Saman is Dr. David Babson. So David has been launching a lot of very exciting programs from government agents. So he has worked at EPA, at DOE, at the USDA, and recently he is currently he is a program director at RPE at DOE. So he has organized many very good programs in carbon conversion, efficiency, and data. Welcome, David, to come here. And last but not least is our own professor, Professor Mengdi Wang. So Mengdi is a associate professor at operational research and financial engineering at Princeton. So she has been really an emerging star on data science and using data science to solve a lot of industrial and our different issues. So with that, I'll welcome the panelists each to give a short presentation, a few minutes and few slides, and to get their takes on like how do we use data science to navigate water and energy fields. And then we'll have a few questions and we'll open up the floor for your inputs. All right. Our next slide is where is it? Control room, I'm looking at the control room. There you go, Mengdi. You have a, yeah, you just use the microphone, sit here, yeah.
Okay, so I guess my role here on this panel is to be the AI person. So I'll talk about basically pure AI. And a particular, thank you. And a particular area of artificial intelligence that is really changing the landscape of this field and maybe potentially many other fields. So reinforcement learning. So I'm a faculty at Princeton, and also I'm having a joint position at Google DeepMind. So hopefully we're using our academic research to accelerate artificial intelligence and also to use artificial intelligence to solve many existing problems and even create new problems and solve new problems. Okay. So first, so what is reinforcement learning? I guess many of you have heard of the amazing success of AlphaGo. Basically, this Nature feature paper like a few years ago by DeepMind, like how to actually solve one of the most complicated game by computers. So if we think about this, so really, reinforcement learning is the core technology behind AlphaGo and many other advances beginning in game AI. And later, reinforcement learning is used to, for example, control self-driving cars, to make daily decisions in trading, in e-commerce. And recently, DeepMind has this very impressive result on StarCraft. So basically now computers can team up and achieve master level records on StarCraft, which is again one of the hardest team game for humans. So now what is reinforcement learning? Reinforcement learning is about using computers and using mathematically driven algorithms to figure out control policies or to figure out decision policies for complex environment in order to maximize some objective function. Okay, and you guys might look at me and feel like, okay, so okay, you look smart, but why do you work on games? I mean, games are like so childish, right? So I think my answer to this is, so if we think about like a baby, a human baby is going to first learn to recognize faces and learn to speak. And this is what computers have been trying to do, right? Recognize faces, recognize images, and then learn to talk. So now computers can already do so. But the next step for a human child to learn to become more intelligent is through playing games. Because games are well-defined environments. And child can learn how to explore and how to figure out complicated decisions before we can actually let a child maybe become a lawyer or a doctor to make actual decisions. So I think game AI is actually this current stage of artificial intelligence, which is necessary for computers to practice to make complicated decisions. Okay, next slide. Okay. What did I write there? Okay, so what is reinforcement learning? So reinforcement learning is a combination of, I would say, a large number of technologies together. So at the core, reinforcement learning is about feedback control. So we look at the state of a game or the state of a complex system that we want to control, and then we try to figure out what is the next step. So the core is control, but the technologies actually include basically all the advances from data science, from machine learning, from computer science. For example, in order to really navigate in a complex environment, we need to do dimension reduction. We need to learn structures and patterns from high-dimensional data. And also, we need deep neural networks to scale up high-performance computing. We need deep value function networks and deep policy networks to be coupled together to adapt and to iterate and learn from data and to bring up the intelligence to the next level. Okay. And also, in order to really scale things up, we need parallel computing. We need a lot of GPUs linked together to work together. We need GPU servers to actually learn against each other to do self-play, for example, to solve a two-player game. And also, we need a lot of other technologies. For example, if we want to learn how to drive a car, then we definitely will need computer vision. We need technologies from computer vision that will be input to the reinforcement learning system. And they have to be combined together seamlessly to get the best performance. We might also need natural language processing. We need all the advanced sensing technology to really make things work in a robust way. Okay, so basically, I'm supposed to talk about AI. So let's really think about what is reinforcement learning and what is AI doing. So really, AI comes from classical control of complex systems. So at the very beginning, I would say I think control theory was developed around the Second World War. So basically, control used to be about a known physical system, maybe the missiles, or maybe some to automate certain, a simple example would be the inverse pendulum, and then robotics, and then automation in manufacturing, and aero engineering. So basically, control is about, for example, if I have an energy grid and I have partial differential equations to model everything precisely, and then can we compute the best policy to control it? So this was control. And later came machine learning and data science. So what is machine learning and data science? It's about, okay, now I have something very unstructured, maybe like images. And now we want to recognize faces. We want to identify maybe connectivity in this voxel network in our brains. And maybe we want to know there's a person on a bike, and we want to understand those relations. So if we think about machine learning, it's really about we do have high-dimensional unstructured data, but we want to learn some static mapping. So I can look at X and try to predict Y, and this is static. So now, what is reinforcement learning? Reinforcement learning is about putting control and machine learning together. So we no longer have a well-defined, known physical system. So the system we talk about can be just much more complex and much bigger, or just something that I cannot describe. Maybe the only thing I can say about my system is, okay, I have all this sensor data. Let's try to do something. Maybe it's hard to actually model the underlying physical system because we cannot measure everything. Okay, so now reinforcement learning is about to take advantage of machine learning and data science and try to explore and make decisions in unknown dynamical environments. So that's where we are. Okay, just to give you some idea about how efficient reinforcement learning is today. So on the left is a very childish Atari game called a Demon Attack. Yeah, it's about we want to control this cannon and try to shoot some demons on top of it. Okay, so suppose that I have a reasonable algorithm. I try to train it on a GPU. And I tune some parameters, and I play with my neural network. And it might take 2 hours to get superhuman performance, which is not too bad. But however, if we actually think about the training time in human time, so the number of games this computer has to play to get to this level, so the human time will be more than a month. So that means that the computers are really not smart enough. If we ask a kid to play this game, the kid can learn to play it in a few minutes. Okay, and things becomes even harder for complex robotic systems. So to make training actually work in human time, it might take 1,000 years. Okay. So if we try to push this technology to real scenarios. For example, in finance, we care about trading and portfolio management. And for example, in healthcare, we care about can we figure out the best clinical treatment policy from data. So in all these applications, we do not have the perfect simulator like in a game. So then data efficiency, computational efficiency, and robustness are going to be super important. Okay, so something that my own group has been working on is we try to improve the efficiency, the sample efficiency, and the generalizability of reinforcement learning. So for example, like we had a few papers at top machine learning conferences in the last couple of years, and we can show that if we have a planning problem of 100 steps, meaning that we have to make 100 sequential decisions. So for this problem, we can actually improve the efficiency to, I think, 10 to the 8 times by just trying to develop better algorithms to take advantage of underlying physical and mathematical structures of the control problem. And we're able to achieve the same level of accuracy and robustness by using maybe only 1% of the data that was needed by the past state-of-the-art algorithms. And other things we try to do is we try to understand how to do reinforcement learning in complex environment by identifying the underlying phase space. And then we can figure out strategically what are meaningful states. We can actually learn what states of the game are meaningful strategically. Okay, and another important area is in order to actually make reinforcement learning work on a complex systems that humans have worked on a lot, we need to be able to imitate human experts. And we need to take advantage of humans and their knowledges and in order to improve them. So that's called imitation learning. Okay, so basically reinforcement learning has a lot of applications. For example, if we want to teach computers to write an article, writing an article is actually a control problem because it has to write the article word by word, and there are certain objective functions like I want to convey a certain message, and the article has to be coherent. So we can actually make reinforcement learning to work and to write articles. And reinforcement learning also applies to quantitative trading. For example, if we think about high-frequency trading, then there are a lot of problems like market has certain hidden market impact that can never be modeled or back-tested using existing data. So a high-frequency algorithm has to really adapt in the real market at the risk of losing money, and then how to quickly adapt and how to quickly learn the optimal policy. And this similar phenomenon also occurs in portfolio optimization. We can use reinforcement learning to keep refining the model of the market and try to adjust the portfolio. Okay, so basically, reinforcement learning can be applied in my mind, all possible fields. And so we want to make it to happen. And so this is my group. And so right now we're working with the Andlinger Center on trying to use RL to solve complex control problems and decision-making problems in the water industry. And I look forward to the discussion.
Thanks so much, Mengdi. You can see even for me, what Mengdi was talking was like right here, right? So that's really, we want to assemble this panel to understand how do we find the synergy to really using all these cool tools to apply to water energy system. And with that, our next panelist is going to talk about, I'm waiting for it. Yeah, for the slide. Because I don't know the order when they upload it, but it doesn't really matter in terms of sequence. There you go, David. See, we won sequence. So David's going to talk about really the nexus of complex systems, energy, water, food, and the data, right? So I'll give it to you. Yeah.
We'll keep it focused on that.
Okay.
Thanks for having me. Let me just dive right in. What is RPE? I always have to start with this. RPE is an independent agency under the Department of Energy. It was modeled after DARPA. Most people are familiar with the Defense Advanced Research Project Agency. That was the model. And this research agency focuses on high-risk, high-reward, moonshot types of programs. The structure ensures that there are new programs all the time. Program directors that come in, like myself, are appointed for 3 to 5 years, and then we have to leave. So we're always looking for new people, and that ensures that we always have fresh ideas and we don't have any legacy programs. What types of problems are we trying to solve? Of course, what you would expect from the Department of Energy. We want to make sure that we have a resilient, sustainable grid. We want to ensure that there's economic prosperity. We want to have energy resiliency. And the thing that I think about, the thing that I worry about, is climate change. And yes, your government is still thinking about that and working on that. Our programs have traditionally fit into these 3 categories: electricity generation and delivery, efficiency, and transportation. And I want to, with my programs, expand this table to include ag tech, biotech, and carbon management specifically. So the new programs will really focus on that. One thing to note about all of RPE's programs, they're really into acronyms. The names of all these programs here, which are too small, they have like a name, for example, like Terra. You'll be like, oh yeah, that works on land-based stuff. I'll talk about this program later. Or Roots, they work on Roots. They're also an acronym, and don't ask me to know what all of them are. But nevertheless, that's something that's very big to RPE. Now, we are a relatively new agency. We actually were just authorized to get money in the 2009 stimulus package. That was when we were first established, really. And so over the past 10 years, we've spent about $2 billion. We've funded a bunch of research projects. Those have, spun off into startups and led to a lot of patents and papers and all those different things. The cool thing about RPE is that it has been growing at a clip of about 15% per year. So we are always, despite the current administration, every year the budget for RPE is always $0. But Congress always comes back and adds, the funding that we had the year before plus 15%. So for good measure. And so we're growing, expanding, and doing really cool stuff. So let me dive into the actual content that I came here to speak to you about. This plot is really important, and this is something that says a lot in one graph about the challenges we face, the resource challenges that we have to address. The center line here, and this is not my plot, I got this from the National Academies of Science. The center line here, the red line, is the path that we need to follow to keep global temperatures below 2 degrees of warming. The thing to note here is that we need to, achieve net neutral emissions or zero emissions by just after mid-century, and then we actually need to go negative. We need to begin to, as an economy, be able to remove more carbon than we put into it. And below the zero line, this blue area under here, those are negative emissions. And you will notice that the contribution to the net emissions, the red line, are significant well before the crossover point. So we need to begin immediately establishing and growing a large, robust carbon removal industry. So when I talk about the discussion around the food, energy, water nexus is about how we use resources in a dynamic economy. And one thing to keep in mind is that we need to build a new industry. And so we must contextualize the challenges that we think we face in terms of food, energy, and water to actually grow and expand to support a very, very, very large negative emissions industry. And beyond climate change and carbon, of course, we still need to worry about feeding people. We have the challenge of a growing population, growing affluence. In and of itself, that is not a problem, but it is something that we need to understand changes the demands for resources globally. And then we have the fact that we have limited land. With current growth practices and our capacity of our ag sector, we would not be able to feed everybody on the planet in 2050 without innovation. In fact, this plot highlights the fact that there would be a productivity gap if we were to just expand agriculture with current technologies. The number of calories that would be able to be generated versus the number of people that would need calories do not match. So we need to innovate and actually develop new strategies that produce more yield and are more sustainable. let me get back to this point of the negative emissions industry because it is enormous. By 2100, we will need to have the capacity to remove 20 gigatons of CO2 per year. Just how big is 20 gigatons, to give you a sense? The US trucking industry, all the materials that flow on the backs of trucks in the United States per year is only 9.8 gigatons. All of the materials that flow through US pipelines would add another 3 gigatons. We would have to add on top of that global cement production and global iron ore production to get somewhere in the ballpark of 20 gigatons. That means that the largest industry on the face of the earth in 2100 is going to be carbon removal and management. And so we need to innovate in a number of areas to be able to address our food challenges, our water challenges, our resource challenges, and to build this largest industry to address climate change. And the drivers for innovation are our capacity to remove and manage carbon, to save and spare land, and of course our water resources. I will note very quickly that in the case of both carbon and land, they need to become negative. And when I say land negative, I mean that we need to slow the rate of transitioning land to ag down to zero and actually get to the point where we can return ag land back to natural habitats or to feedstock production of carbon efficient things for a growing bioeconomy or for carbon management and ecosystem services. And there's a lot of work to be done in a number of areas. I won't go through all of these, but these are the areas in which we are funding immense amounts of research into all of these different systems. And my program specifically focused in 2 areas. One is we live in a carbon-based economy. So therefore, how are we going to produce all of the carbon-based things that we need, these plastic-covered chairs out here and carpets and fuels and those things that are carbon-based from renewable carbon? How do we manage carbon in the economy? And then also, how do we manage to get carbon out of the economy? All of my programs fit into those 2 things. And I will give you the context for the data that we need to talk about. And the future economy won't be so much low carbon as it will be new carbon. So we need new technologies to be able to actually use our carbon resources efficiently and make our economy itself a tool for managing carbon instead of the excuse for not managing it. Gosh, that's a tired excuse. And the way we do this is through the bioeconomy concept, where we source renewable feedstocks, renewable carbon, and then connect those with conversion technologies to deliver the products and fuels and chemicals that we need for a growing low carbon, negative carbon economy. And so the technology that we're developing in that space where I said was the carbon management. We need innovations up and down the supply chain. So when I came to RPE, I took over the Terra and Roots programs. I'm going to talk really quickly about this how we improve feedstock production practices on farms. And that's through my Smart Farm program. The Smart Farm program seeks to develop all types of new sensors and systems that can go into the production of ag crops so that we have better information and we can actually enable a future highly precise precision agriculture system using things like AI that can collect data and actually make data packages so that we can have really efficient systems. The way that we're going to actually finance this is by connecting farms to established carbon markets. I won't talk about these other 2 programs because I have very limited time, but the center program is called EcoSynBio. This program actually seeks to leverage low-cost, low-carbon power to change how we convert things. Imagine instead of when we do, like say, everyone knows this reaction. It's the production of ethanol via fermentation. So sugar goes to ethanol and CO2. What if we could change that reaction chemistry to sugar plus a reducing equivalent goes to 100% ethanol and the balance being water, where all of the carbon in a feedstock goes to product? We would be able to grow the size of our bioeconomy by 50% without using a single additional kilogram of feedstock or another square inch of land. So that program is really an interesting one. And then, of course, NEAT is the one that will service that largest industry that I talked about. Now, quickly on the data programs. Terra and Roots were programs that were designed to develop sensors that could give good information about crops, both above ground, the things that we can see and the way that they actually grow, and below ground, their root systems, how big roots can grow, how much carbon they can store, and those sorts of things. By developing the data to understand how plants grow, we are able to more rapidly engineer crops for a future economy that are more carbon efficient and to make them more resilient to climate change. In the new program, Smart Farm, yeah, that is the acronym, and I'm not going to even read it because we're over time. The goal is to understand that biofuels, and the reason we focus on biofuels is because there's already an established carbon market. Biofuels are more valuable the lower carbon intensity they are, because you get paid for the difference between the carbon intensity of your biofuel and the petroleum baseline. So if you could make this, you know, net neutral or even carbon negative, that difference becomes much greater and it becomes more valuable. And we think that feedstocks, the actual production of feedstocks that feed into bioeconomy supply chains could be carbon negative. And in order to do that, farmers would need to adopt new practices and new technologies, but they would need incentives. The incentives that they would have to drive down emissions and then drive, you know, more carbon into soils is through things like the low carbon fuel standard that has an effective carbon price of about $200 per ton. And so in order to connect farmers to this, we need to develop better capabilities to quantify GHG fluxes on farms. If we could develop the sensors and systems to quantify field-level carbon intensity, we could connect farm practices to carbon markets and deliver significant sustainability improvements across the ag sector. So that's the data challenge. One, I do have to make this quick pitch because I'm here at a university where there's all these people that we need. Consider coming and working at RPE. A lot of professors become program directors for some period of time because they can take a couple years, come and run a program, and then come back to their universities. We need new ideas. There are opportunities for people that are PhD students because we have like a postdoctoral program called our DOA, our Fellows Program. And we have opportunities also for tech-to-market advisors, and we have opportunities for undergraduates and graduate students as well. So consider coming working at RPE. Send me an email. Here's my information. Happy to take questions later, and I'm sorry that I'm over time. I know it stresses you out. And I apologize.
Thanks so much, David. Let's give David a big hand. So, very relevant, what you just said, certainly all the nexus between food, carbon, water, and data, and energy, right? So in the afternoon session, we'll have a specific panel discussion on carbon valorization. So that's really very tight together with the morning program. So very good remarks. So our next panelist is you, yes, Saman. So and you will appreciate actually you coming here from Bay Area and really to give us some insights on private entrepreneurship opportunities.
Yeah, it's really an honor to be here, actually. I think I feel a little bit like the odd duck here, you know, like the one from, you know, the evil capitalist trying to make money off of all this. But I think really seeing what's happening in the startup world and seeing a lot of the practical implications of a lot of the work that everybody here is doing is actually very inspiring for me personally, and I think hopefully after this I'll share some examples. Hopefully it'll also give everybody some more ideas. So just to connect a little bit of what Mengdi started talking about around AI with specific applications, I think maybe first I'll just start with a little bit of context in terms of the way that we see things and kind of what practical impacts AI really has on the way that basically humanity does production in general. So obviously it's a very, very big topic. But like the standard model I think everybody's very familiar with is there's a lot of essentially human decision makers in every part of the process. So that includes human analysis of quote unquote data, which generally is a very low bandwidth endeavor where people can process certain amounts of information and then they use their own experience or expertise to try to make a decision. In the best possible cases, that experience is maybe 80 years of experience, which compared to the possible training that an AI model can have is almost nothing. And at the end of the day, whatever decisions are made are also implemented at a very low efficiency. So even though we may have the best policies and the best systems that are designed, at the end of the day, what really gets implemented usually has a very large gap from that. And I think there's been a lot of schools around academia, like Six Sigma and whatever, that have been trying to get us closer to that ideal decisions that we make and how we can carry them through. But the reality is that it's still very far in most cases. But what's really happening with the emergence of AI is it's a few forces that are happening at the same time, but one big one ultimately is just drastically larger amounts of data. So sensors are everywhere, and the number of them is increasing exponentially. We were talking yesterday at dinner about portfolio companies that we've invested in that are making sensors that are a couple of cents, that are millimeter size, that can be ingested into the human body or implanted into a piece of machinery. It will last 8 years with a tiny solar panel on it without ever needing to recharge, and will be constantly sending data. So as those types of things happen, like we call it the smart dust, it really is going to be ubiquitous in everything. And the dimensionality of that data is going to just increase. It's not just the scale and number of them, but also the types of things that can be sensed are also drastically increasing with a lot of technologies that I won't talk about right now. The other side of it is with that drastic increase in the amount of data that's collected, the human decision-making becomes even more inadequate. So we have systems like what Mengdi is working on around reinforcement learning that can take large volumes of data and very quickly turn it into a control scheme, whether that's in an industrial facility, how to control the valves and the pumps in a water treatment plant, or whether that's making insurance claims, or whether that's sorting recycling, or whatever it might be. There's just many pieces of those decisions that have to be made, and all of those decisions can be made at the level of the best imaginable decision maker, because they can take lots and lots of experience and train it across, and then they can learn from their mistakes in one geography and apply it in many others. And then finally, I think there's the implementation side of it. So these control systems are becoming so good now that robotics is kind of a very general term. It's not necessarily a humanoid robot or a robot arm, but actually kind of even a smart building is a type of robot where there's inputs and then there's outputs. And these robotic systems are becoming much more sophisticated. They're moving from the previous model, which was rule-based systems, to much more intelligent decision systems. So this entire chain is changing the way that production is done in kind of every context. And so moving on to the next slide, specifically if we talk about an example around like process manufacturing, when we think about decisions, right now a lot of decisions are made a few times per day, or maybe 1,000 times per day in a really efficient process. How do we increase that to millions or billions of decisions per day? And that allows us to go from very general purpose decisions to decisions that are very targeted towards specific cases that come up. The other part of it is equipment itself becomes much more efficient because it becomes usable in many more contexts than before. So a robot that in a traditional car manufacturing facility can only do a specific operation repeatedly, with intelligence now it can actually perform multiple tasks. And so it completely changes the layout of the factory. So instead of having a linear process where things move from one stage to the next, you can actually have this matrix where parts can move kind of arbitrarily through the facility wherever there's spare capacity to produce things. And so the overall productivity of any industrial process goes up a lot. High-frequency testing and analysis, I already talked about this with the sensors. On the bioengineering side, there's also a lot of really exciting work that's happening. I'm not an expert, but I think that there's been a lot of really cool examples of companies that have been doing interesting work. We have a company that we've invested in Boston that's using AI to predict the physical characteristics of new molecules that it's predicting, and then in a lab it automatically synthesizes all of them, and then it tests all of them, and then it feeds that back into the model to improve its prediction. And so what that's allowed it to do is instead of what a human scientist might do is screen a few molecules over the course of a few years and study all of their properties, their system now is getting it to the order of magnitude of thousands of molecules per day, moving towards tens of thousands of molecules per day. And so that drastically increases our ability of finding materials that are appropriate for different use cases. The next one is kind of efficiency of coordination. So that's another one that I already kind of alluded to before. But essentially, when you have this many moving parts in any process, whether it's the economy or whether it's in a factory, the number of parts that have to work in synchrony with each other is much more than any human can possibly comprehend. I think there was the example somebody gave a few years ago about there's no single human being on the planet today that can actually tell you from end to end, from raw materials, how to make a pencil. That's a very, very simple thing, but from the graphite to the wood to the paint to all the things that need to be made to make a simple pencil, there's no human being left in the world who actually knows how to do all of those steps. And let alone the much more complex things that we create on a daily basis. So how do we have AI systems that really can understand the entire process and coordinate them much more efficiently? And there's many other things, just keeping track of time. I won't go through all of them, but inventory can be much more efficiently managed as well. So the next one, agricultural applications of water is a great example of this. I think we see a lot of companies now that are working on using AI to do intelligent decisions in agriculture. The simplest versions of that are, instead of watering the entire plot with the same amount of water, how do we kind of target it based on the actual sun exposure and the actual genetics of every plant, and this is an example of granular decision making. Instead of making one decision about the entire plant, how do we make a decision about each particular plant and how we water it? But there's also a lot of second order effects that are very exciting. For example, we have a company that we invested in that does automated apple picking. So this is a pretty simple task. It sounds kind of trivial. It's like, oh yeah, instead of human labor picking apples, we now have a robot doing it. But actually there's a lot of interesting second order effects. For example, because right now most of the labor used for harvesting apples is brought from short-term immigration from Mexico, they usually can only bring them once a year. And because they only bring them once a year, what happens is that most of the farms plant a single type of crop that will all mature at roughly the same time of year. And even in that situation, they don't actually all mature on the same day. There's this distribution curve of when they mature. So whenever you pick it, there's still roughly 50% of the crop that's either overripe or underripe. When you have a robot that can do that every single day and pick exactly the fruits that are ripened that day, not only does that increase the productivity of the entire farm, but also it allows the farmer to now start planting different types of crops that harvest at different times of year. And we've seen that starting to happen already in Washington State, where farms are diversifying the types of things that they're planting. So it's just fascinating to see. And then of course on the waste side, there's also really interesting things about how to forecast and process that waste. Another example, because of time I won't talk about it too much, but this is a company we previously invested in that in a typical water treatment plant there's something like 20 to 30,000 sensors. Most of that sensor data just goes and sits into a file and is never looked at ever again, except if it trips an alarm and then somebody will go and do something about it. What this company has done is they used reinforcement learning, as Mengdi previously alluded to look at all of that data in real time and then generate a control schema for all of the pumps and valves in that water treatment plant, and they're able to reduce energy usage by roughly 20%. And so this is with roughly just about a week or two of training data. So this is something that a typical human operator sitting in the control room could never hope to achieve. And it also makes it much more adaptive to different kinds of feedstocks, which are changing every day. It uses that data to adapt its control schema. I won't go through all these other examples of startups that are out there. There's a lot of very exciting ones. I think kind of going back to my role as a venture capitalist, talking about the types of things that we're funding, we're really, really excited about this next wave of technology companies. I think we think it's going to be even bigger than what happened during the Industrial Revolution. During the Industrial Revolution, I think we think about it as the way that we can take our decisions and implement them got a lot better. We had the strength of 100,000 people in a single robot, or 1,000 people in a single robot. Now we have the decision-making ability of 100,000 people in a single device. So the impacts of that are going to be much, much bigger. So we're very, very excited about those types of companies. All right.
Thanks so much, Saman. It's so exciting to see actually the venture capital firms start to invest in the infrastructure and the food and agriculture related fields rather than just investing in apps and things like that, right? So this is very exciting. Thank you so much. So our next speaker is, it's you actually, right? Is Jeff Moeller. So Jeff will talk about how the nonprofit, the foundation, and their work actually links to the different stakeholders on this topic.
Thank you, Dr. Ren. Let's see if this one works a little better. And thanks to the meeting organizers for the opportunity to be here. Maybe I thought I'd just start with sharing a little bit of background about my organization, the Water Research Foundation, in case you haven't heard of it before. We're a nonprofit research foundation located in Alexandria, Virginia, and Denver, Colorado. We've been around actually for a little over 50 years, and in that time conducted about a research portfolio valued at about $700 million, including 2,300 projects. Our focus is really to advance the science and technology of water, to protect health and the environment. And when I say water, I include wastewater, drinking water, stormwater, water reuse. Most of our funding comes from our subscribers, and our subscribers are primarily water utilities. It includes drinking water, wastewater utilities, public agencies, cities, counties. For example, the City of Philadelphia, New York City are members of our organization. So we're really coming at this from the end user perspective of water. We don't do the research in-house. We fund and manage research projects. So for the, I guess, the students and the faculty out there that are looking for research funding, I encourage you to visit our website there to look for opportunities. And our organization, just in terms of give a sense of some of the research priorities we have about, we've been working with, cities and water utilities to identify what are their needs, what are their priorities, and have identified this baker's dozen list of research needs. So these are our research areas that we have. Around each of these areas, we have a strategic plan and a suite of projects that we're working to advance science and knowledge on these topics. And as you can see, energy production efficiency and intelligent water systems are high priority items on this list. In terms of energy and wastewater, a few years ago, we did a research project to look at what's the energy content in wastewater, and determined from that effort that wastewater actually contains about 5 to 10 times the amount of energy needed for the wastewater treatment process. A lot of this energy is embedded in thermal energy. It's kind of a low-grade heat energy. About 20% of it is in chemical. That's the organic content that's in the wastewater, and about 1% hydraulic. Most of the efforts so far have really focused on that 20% in terms of trying to recover that energy there. And there are now in the U.S. a handful of examples of wastewater utilities that are either energy neutral or energy positive in their treatment processes because they're tapping into this embedded resource. It's also helping to drive a paradigm shift in the wastewater industry. Historically, a lot of utilities around the country have really just been focused on meeting their permit limits, treating the wastewater, discharging it back out into the environment. But now they're beginning to understand that wastewater contains really valuable resources, primarily in the terms of water, energy, and nutrients, that can be recovered and reused. So as you're aware, in the circular economy, there is no waste. There's just resources that are not being used or underutilized. So it's starting to shift in the industry. The Water Environment Federation a few years ago changed the naming nomenclature for wastewater treatment plants and started calling them water resource recovery facilities. It's a little bit more of a mouthful, but it's just trying to drive home that sense of these can become factories producing products. And not only the three that I mentioned there, but there are also researchers looking at recovering bioplastics and valuable chemicals from wastewater, or even metals. An important component of that whole effort is smart systems and using the data that's out there. But one challenge for a lot of these utilities is that in terms of big data, the utilities are kind of left scratching their heads, They don't really, they're actually generating tons of data points. In many utilities, they're gathering, thousands, if not tens of thousands or hundreds of thousands of data points, but they don't really have the slightest idea what to do with it in many cases. So we're working to, I'm going to give a couple of examples of three examples of some research projects that we have going on that's working in this space to help illuminate how utilities can tap into data science to improve, reduce energy consumption and costs. So timing for this project actually fits well with the timing of the meeting today. This is a report that's in publication right now, so it should be coming out in the next month or two, looking at managing water and wastewater utility data to reduce energy consumption and costs. This project really is looking at developing and providing guidance on effective strategies for water and wastewater utilities. by focusing on identifying what are those data sets of value to reduce energy consumption, including cost of pumping operations and treatment processes, and then looking at how do you use that data, data acquisition, storage requirements from various information technologies and energy management systems, and then what are the analytics and platforms and display methods that you can use to support business decisions at your utility. The project also includes about a dozen different utility case studies of ways they've employed data science to help reduce energy costs. So this is a conceptual schematic of a holistic data management solution where on the left side you have your data lake, if you will, all the different types of data sources. And at utilities, it's a large set of data that they're pulling from their labs, treatment process data, field data, other data from their, including financial management and asset management systems. Taking that data and putting it into a data management system where you can start to use analytics, everything from simple statistics to advanced analytics to predictive analytics on up to the highest level of machine learning or artificial intelligence, which some of the other speakers have talked about. And using those analytics to inform your business decisions and using graphical displays to help make it easier for you. So this type of schematic that I'm showing here, it's been widely used in other industries, automotive industry, food and beverage industry, mining industry, but the wastewater industry, has been implemented very little so far. So there's a huge opportunity here in the wastewater industry to advance the way we approach things. Two other projects, these are newer ones. One just started looking at application of big data for energy management and water utilities. And then there's another project, we just had an RFP out about a month or two ago, so we're in the proposal selection process. But looking at how to be a digital utility and developing a framework for intelligent water systems. So coupled with our research program, we have a program at the foundation called LIFT, Leaders Innovation Forum for Technology, and it's a program focused on innovation with the goal to accelerate research, innovation, and new technologies into practice to help move these things into practice more quickly. And I'll give you just a couple of examples. I'll highlight three in particular of some activities that we're doing in our innovation program to help advance these types of solutions. So the LIFT program at its heart has a utility peer-to-peer network. We've got about 700 utilities that are working together to share information on different topics, including we have a focus group on intelligent water systems and one on energy management. We're taking advantage of the fact that these are public agencies and they're more than happy to work together and share information. We also have a program on technology scans, which are we have basically a technology scout on our staff that's looking at innovative technologies in the water industry. Those technologies we load up into a platform called LiftLink. So we've got about 150 different innovative water technologies that are in that platform right now. And then we have a program called See It, where we provide travel scholarships for utilities to go and see innovative technologies in practice and bring them back to their own utility for adoption. I'm going to highlight these three at the bottom for a little bit further, deeper dive. We do have a program to better connect universities and utilities. One thing we've seen in the water industry, we have, in some cases, a lot of universities developing solutions that are looking for problems, and you have utilities with problems that are looking for solutions, but they don't always connect. The chair of our LIFT program, Dr. Sudhir Murthy, who used to work at DC Water, he was the chief of innovation there. He went to Beijing once to visit a water utility there. And while he was there, he saw all these students working on different demonstration projects at the utility and working around. They actually even had almost like a dormitory where the students would sleep at the water utility, the poor students, so they could work 24/7 on their projects. I don't know that we're necessarily advocating to build dormitories at wastewater utilities, but we do think there is a there is a good opportunity here to better embed students at utilities for solving real-world problems, and a whole host of benefits there for both for the universities and training students, and then also for the utilities in gaining new insights into their problems and training the future workforce that's out there. Two last items on the LIFT program. As Dr. Jason Wren mentioned at the beginning, we have been working on developing a national testbed network for water utilities. And we've been working collaboratively with EPA, NSF, and DOE on that effort. We started with developing a testbed directory, and that's available on our website. It's publicly accessible. We've got about 100 facilities worldwide so far that are participating in this. Everything from a level 1 facility, which is a university lab or a DOE lab, on up to a level 4, which is a dedicated demonstration or test facility. And you can click on each of those points in there, and it'll pull up an information sheet on that facility, so that the point is to help better connect entrepreneurs and technology developers with test facilities appropriate for their needs. And the last activity I'll share that we have going on under our LIFT program is something called the Intelligent Water Systems Challenge. We've done this the last 2 years. We'll be doing it again in 2020. And this is where we've launched a challenge to help focus on leveraging data that's out there and using the best available tools to help utilities better understand the complex systems for better decision makings, and to, in particular, help engage students, universities, and new technology providers with utilities and demonstrate how they can be implemented at utilities. So our first year we did it, we had about a $50,000 prize for the winner. Again, we'll be doing it in 2020 and encourage folks to participate in that effort. So there's my contact information if you'd like to discuss more. Thank you.
Thanks, Jeff. A quick follow-up on Jeff's talk, because what prompted me to propose to organize this panel is my class and we visited a treatment plant in Elizabeth, North Jersey, and the superintendent told me, like, okay, so every 10 seconds, we generate 300,000 data points on one single plant utility, and we don't use any of the data. It's just put in the cloud, and there's really not much we do. So then I realized I talked to actually my colleagues in research arena. Nobody is really working a problem like this. So that's why Jeff and I and other folks, recently we put together a major MRI proposal to try to establish a cyber infrastructure for water data analysis. We actually gathered 6 universities and 6 big utilities, water and wastewater, across the nation to really try to establish an interface. I hate to use an analogy like the Facebook type of things to really to actually allow the different stakeholders to be engaged together. Utilities will provide data, so they will be the end user of the data. The academia and entrepreneurs, innovators will be able to access data, develop tools, and the students and actually professionals will get trained, right? So that's really, there's no such infrastructure available in the nation, in that matter of fact, in the world. So that's really, we are trying to establish that. So if any of you actually have interest in partner with us, we'll be happy to talk to you. So this is really I think is much needed effort for our nation to really revolutionize our water infrastructure. We're sitting on the gold mines of the data. We can actually do something on that. With that, actually, we have Professor Lee going to give a talk specifically on her actually work on using data science for water industry.
It's a pleasure to come here and give a little bit talk about the work we're doing related to water and wastewater infrastructure. I apologize that some of the slides don't seem to be displayed properly, and hopefully the main contents are still okay. Jeff actually laid out a really nice background on the type of water and wastewater systems we are also working on. I wanted to first give you a brief background or introduction on our center. Our center is called Nanotechnology Enabled Water Treatment Center, and it's a National Science Foundation funded engineering research center, and our goal really is look at how we can change the way we treat our water and wastewater for optimal water and energy efficiency. As you can see here, it's a fairly large scale center, and a difference between most of the other centers and engineering research center is that we actually work with the industry very closely, and the main goal is to develop an innovation ecosystem that would quickly take laboratory findings towards commercialization products through that interaction with the industry. at the beginning, our goal really is to develop technological solutions. We're trying to change how we've been treating water and wastewater traditional approach of this very large-scale chemical reaction-based method, moving away from that instead towards more flexible, more adaptable, smaller scale treatment systems that are based on physical process and catalytic process so that we can minimize not only energy consumption but also waste production as well. And so we are trying to address primarily two different challenges in urban water systems. The first one is the increasing gap between our water demand and our water supply. Not process my slides here. Because of the rapid increasing in global population and also because of the impact of global climate warming. And another challenge we're trying to address is our aging infrastructure worldwide, especially in large cities where our water and wastewater systems are getting old and they're breaking and they're also letting in contamination in our drinking water. And so that leads to very expensive maintenance needed for most of our major cities. And we do see those as challenges, but also a great opportunity to take a new look at how we've been supplying water to large urban systems and look at how our new treatment process can be implemented and also look at what system level changes we should make. So our vision is really that instead of following the 100-year-old centralized water supply approach where you take a centralized surface water source and you treat it all of that water to drinking water quality, and you send that drinking water through a very massive distribution network in which you have deterioration of water quality, you have leakage, which leads to loss of water, and then use that water to flush our toilet, wash our cars, and water our lawn. Instead, we propose a hybrid system where you still have some of that centralized supply, but we don't treat it to drinking water quality. Instead, we treat it to a quality good enough to distribute through the network to these different, what we call local operation centers, where we would then supplement net surface water supply with locally available alternative water sources, including our reclaimed wastewater, our storm water, and if you have brackish groundwater, and those cheaper, more closer water supplies and treat them to the different level of water quality that would fit our local water demand need. So the question for utilities would be, okay, what do we do? Do we use this water for drinking? Do we use this water for non-potable applications? How do we build our infrastructure system? How many of these operation centers? So a lot of questions that are really dealing with the system level configuration, which we weren't initially trying to address because we were originally trying to develop technologies only. So that's when we got into this field of large water and wastewater infrastructure. How do we utilize the data that currently available from our existing infrastructure systems, and how do we envision this future design of new water and wastewater infrastructure systems, and what kind of analytical tools and computational tools can we develop to help the decision making in order to come up with the optimal infrastructure, water and wastewater infrastructure system that would give us the best water efficiency, best energy efficiency, minimizing waste production, and best water quality that can be used for different purposes. So we did a case study working with the city of Houston. The city of Houston has a massive water distribution network because our city is very, very spread out, and all our surface water supplies are on the east side of the city, and our population growth is mostly on the west side of the city. So from an energy point of view, it really doesn't make sense to pump water all the way across the city if you have more local water supplies on the west side of the city. So one solution is really, can we take wastewater or stormwater that are locally available and treat this water and to supply to these populations that are further away from the surface water systems. And you can see here another interesting fact about the city of Houston is we have a huge number of wastewater treatment plants. There are currently 39 wastewater treatment plants. All of this could potentially be a new water supply sources. And so we took these wastewater treatment plants, and we imagined that if they can treat that wastewater through advanced treatment technologies and supply water for potable or non-potable purposes, and how would we change our overall energy and water efficiency of our system. So this is our overall schematic of the decentralized water supply system. And the first strategy we consider is decentralized potable reuse. So we take the wastewater, we treat it to drinking water quality, and that way we do not need a dual pipe system. And how would that, what would be the energy and economic and environmental implication of this particular scenario? So if you look at from the energy point of view, obviously we care about meeting the demand. So the bottom line is that all of the scenarios will meet the overall water demand of the city for every individual end user, and also meet the water quality requirement as well. So if you look at the energy implication, really we could save a significant amount of energy that was used to pump the water from our surface water treatment plant on the east side of the city towards across the whole city. Overall, however, our energy use goes up because we're putting in highly advanced treatment process to treat that water to potable water quality. All of that water is still treated for drinking purposes. And if we could, however, design our system properly, there are some system configurations that would allow us to reuse some wastewater and still save energy. As you can see here on this plot, we did analysis of all the configurations that are possible through our distribution network and with our existing wastewater treatment plant. There are some designs that we can utilize that would save us a significant amount of fresh water and still be able to save energy. And in terms of technology, as I mentioned, our center's main goal is to provide technological solutions. Right? We wanted to know how energy efficient this future technologies should be in order for this whole new scenario make sense. And so you can see here a sensitivity analysis that shows we're not actually too far away from that goal of having all technology solutions implemented and still be able to save energy system-wide. If you can get down to about 1.15 kilowatt hour per cubic meter of water produced in the advanced treatment process we put in the wastewater treatment plant, you can really design a system with all the wastewater supplied for potable applications and still be able to save energy system-wide. Now, this is from wastewater point of view. Now, in Houston, one of the issues we have is sometimes we have too much stormwater, so we're probably better known for flooding than water scarcity to most of you. We get a lot of stormwater. So another solution is to take this stormwater, which would be easier to treat and would be more less energy intensive to treat than domestic wastewater, maybe utilize the stormwater as a supplemental water supply. And the city has a lot of stormwater data, and they've done a lot of modeling analysis, but most of this is for flood mitigation. Nobody has really looked at this as a potential supplemental water supply. And so we don't have a temporal and a spatial distribution of the availability of stormwater as potential supplemental water supply. So the analysis we're doing now is to look at areas where detention ponds can be made available and look at the temporal and spatial distribution of stormwater and the amount that could potentially be harvested and used as water supply to see if this could potentially be a sustainable solution for us as an alternative water supply as well. finally, once we have this more complicated system where we have so many different water sources and we need to coordinate all of these different water supply points so that they meet our water demand in terms of quantity and quality, how do we make sure that the system is as resilient or even more resilient than the system we have today? So we are looking at this hybrid system in terms of its resiliency depending on the technologies that we're putting in there. One of the tools we're using is we take the large amount of data the city has, we apply simple machine learning tools to model or to predict failure frequency of these hardware, so pipes, pumps, and valves, and look at risk of changing that infrastructure. And so you can see here we were able to, when we compare this new machine learning tool with conventional risk analysis, our accuracy, about 95% of the time, our accuracy improved compared to the traditional risk analysis tools. And so these are basically a few examples of what we can do with data, existing data from water and wastewater utilities. But I do want to conclude by saying that, I kept forgetting, proceeding my slide over there, by concluding that in doing all of this, there really needs a lot of, there's a strong need for a lot of coordination among different government institutions. So we work with many different departments across the city of Houston. We realize how little communication there is between the different government institutions, which creates significant barrier in research and I'm sure in the future implementation of these different scenarios that could be considered. And there is also, as you can see, with little development of the analytical tool, you've already extracted a lot of very useful information. So, but these analytical tools are still not readily available. So I'm sure with further development of analytical tools, especially using AI, we can extract even more actionable information that can be directly used for decision making. With that, I would like to thank you for your attention. Hopefully these examples are useful.
Thank you, Jilin. Thank all the panelists to give really good insights on how do we actually make such complicated systems work together to solve major climate and even local, actually, water energy problems. So I have one question, general question for all of you, so if you can give some thoughts on that, and then we'll open up to the audience to see if you have some inputs or questions on this topic. So my question would be, through like my research and development and working with utilities, I realize this is like we don't have a specific mission like going to the Mars, right? So certainly in a way, we tackle all different type of problems together, and we have to engage a lot of different stakeholders. We talk about funding agency, we talk about venture, we talk about innovators, we talk about education missions, we talk about community engagement. So what's your take? Like, what do you think a good approach for best practice to, again, to make this thing work better, right? How do we actually make an impact by actually gauging interest from different communities and deliver a good solution? I'll start with Jeff.
Yeah, sure. That's a great question. I think that is key. It is key to really bring all these folks together because when you look at it, we're all partners on moving innovation forward. The entrepreneurs, the venture capitalists, the water utilities. So I think we got to attack it from multiple prongs. I think from the utility side, working to better foster a culture of innovation at utilities, and that's one thing we've been trying to do at the LIFT program. A lot of utilities don't really know where to start in terms of developing an innovation program. They've been more focused on just trying to meet their permit limits, keep their operation flowing. that just now they're starting to seize the opportunity, and some utilities are appointing a chief innovation officer and starting to look at new innovative technologies out there. In some places there's water technology clusters, regional economic development initiatives that are helping to provide support to entrepreneurs and to connect them to end users. I think that's really important. I think the one big gap that I've seen that we need for entrepreneurs is a national innovation fund for water. I've seen a lot of entrepreneurs with great ideas get stuck when they get to the point of getting that first pilot, that first demonstration, that first reference. The costs are too large for that small company to take on. The utilities don't feel like it's their job to pay for a demonstration of a technology. And venture capitalists like to come in later in a lot of cases. They like to come in usually when a technology is developing, generating some revenue. So we really need a national water innovation fund to help with those first pilots and demonstrations.
Thank you. Chidi, you have?
To us, I feel like a big gap is also the lack of centralized data infrastructure where clean, the research-grade data can be made available to universities and to utilities who wanted to look at, best practices at another utility, and also technology providers. Small business that have a new treatment technology who have done demonstrations somewhere else, and those data are not available or not considered validated data for utilities are not in that particular state or our city.
Just quickly, we actually entertained the idea. So we have DARPA for defense. We have ARPE for energy. Why don't we create energy for ARPA water? So that's as equivalent as actually water innovation.
Yeah, I don't have a lot to add. I think that what's clear is that the bottleneck is not technological capability. There's a lot of things that will have a very drastic impact, and it's known that they'll have an impact. I think the real challenge is information. There's not a lot of good forums for sharing information. So I think things like today are really helpful. I think the work that the WRF is doing is also exactly aligned with enabling technology entrepreneurs and scientists to actually be able to find real applications for the things they're developing, and also to educate on the customer side with what the latest developments are. So I think that that's probably the biggest bottleneck right now.
I would point out that markets work. To go back to what the congressman was saying earlier, the capacity for us to solve a lot of these problems is to create the right type of market incentives for people to do the right thing. If people could profit from harvesting the atmosphere for CO2 and putting it under the ground instead of profiting from digging carbon out of the ground and putting it in the atmosphere, that would spur the right type of innovation for this to work. I would note that the Chinese are spending $3 for every dollar of renewable energy research that we are spending now. But I would also point out that the analysis that's been done is that it is less than a third as effective because of the closeness of their economy. It is incapable of actually deploying and efficiently deploying those dollars to solve problems. So we actually need to spend more money and allow the policies to create the environment for our open economy to drive solutions.
To connect to Simon and David, so I totally agree that creating incentives is important. So, for example, like I'm working with the healthcare industry. For example, we want to use machine learning to predict better clinical pathway and help doctors to make better decisions. But it turns out that doctors themselves are not a big fan of this idea, because they have their own guidelines and their way of doing things, and so I guess it's natural. But however, medical insurance companies, they have huge incentives because it is their money that they could save. So it turns out that it's actually easier to get data and to actually get something actionable if we try to work with the insurance company rather than actual hospitals. So I think in the energy and water domain, I mean, getting the correct market incentives from either the private sector or government agencies is going to be critical.
It's a very good example because the utilities would have much incentive to actually share the data and improve their efficiency. Very good. Well, let's open up to you guys and to see if you have any questions or comments on this topic. Peter?
Yeah, short question. We talked about infrastructure and new techniques to harvest energy. In the Western world, the problem is that we have a very expensive infrastructure. And can you comment on wouldn't new technology be more likely to be implemented in developing worlds where there is really no infrastructure? The Princeton treatment plant may be $500 million worth. And if you walk up and says, we have a completely new idea for treating your wastewater and extracting energy, we're stuck with that existing infrastructure.
So I guess I could try to discuss a little bit on that. I think the whole point of our research center is trying to develop smaller scale systems, because right now in the Western world, the treatment technologies we use rely on massive infrastructure, very expensive, as you were mentioning, but the same approach cannot be duplicated in developing world. They don't have the finances available to support very massive water and wastewater infrastructure. So point of use or point of entry treatment technologies are better suited for these communities, smaller scale and perhaps more flexible, given that we will be dealing with different local water sources. So a lot of people are working on these technologies that don't require a large centralized facility, but modular systems that you can, just like your cell phone apps, you can put together depending on the local needs, how much drinking water is needed, how much water for irrigation or other purposes is needed, and you can put together a smaller, more compact package. In terms of cost, I think right now we're still not there in terms of the absolute cost of the treatment technology for these small systems. Were still more expensive than the large-scale conventional treatment process, because large processes benefit from the economy of scale. And so there is trade-off, but we save on the infrastructure cost, we save on the transportation, water transport or pumping cost to distribute water through large systems. So there is definitely gain on the cost if you look at system-wide configuration.
So I'll counter you back to look at the energy infrastructure. How many people have argued we relied on centralized energy infrastructure and it's too expensive to replace? Look what we are right now. And the next infrastructure is water. And that's what my mission is. So so think about that. We can change that.
Hi, thanks very much. Actually, that ties in perfectly with my question. So I'm really excited about how these water and electricity systems are going to get more complicated, but also more powerful. And we can use things like machine learning to optimize the power grid, especially as more energy storage comes online, for example. There's a lot of opportunity to smooth out the load. With the water system, I'm sure there's going to be parallels as we have these more of these systems. My question is, I know that the regulatory environment sometimes falls behind. For example, with power, people are trying to build microgrids and to have that pricing work itself out with markets which work, but the regulations don't allow it. So do you have advice for how activists can help encourage governments to do that? How can governments better learn from people like you? And is there enough being done there, or do you have any advice with that?
David, can I give that to you?
Sure. I would just say that it's important to think about the alignment of the regulatory structures with what the goals are. And so there are different levers that are available to incentivize different things. One of the things I would point out about all of these nuanced challenges is that just economy-wide drivers are insufficient to achieve, the things that we want. If you want to have, cleaner water, you need to have a targeted water policy. If you want to decarbonize the entire economy, you need to have sector-specific effective carbon prices that drive down emissions, because in a single economy-wide policy or vague, non-targeted regulations are insufficient. So, advocates for sustainable economy need to focus in on what types of things they want to have and actually develop detailed policy plans to address those things, because it is a bit glib for me to just say, oh, markets work, and people often would think, oh, well, a single economy-wide price on carbon, or paying people for producing cleaner water or something would work. It is actually more complicated than that. So it does require having the large-scale incentives to do the right things, but then the detailed regulatory structures and policies to actually address individual components of the economy.
An obvious source of additional water is, as you mentioned, the reuse of contaminated wastewater. How much experience do we have that anywhere in the world of doing that, and also the psychological acceptance of drinking wastewater?
So that's a very good question. I guess I'll try to, and Jeff can add to that as well. There is plenty of examples of non-potable reuse that's going on with, we reuse water for irrigation, and there's also indirect potable reuse, and you take that wastewater, you treat it clean enough, and then you put it back into a natural environmental buffer, and then you take it out and use it for drinking. But I think in areas where you really don't have many options, people are more open to the option of direct potable reuse. For example, in the city of El Paso, they're actually building a direct potable reuse plant, a very large-scale one. And in the state of Texas, during the drought, we had a fairly extensive drought. Around 2011, there was 4 small cities that actually built potable reuse plants as well, because they didn't have options. There definitely is need for longer-term monitoring of water quality and what are the potential health impact of reusing municipal wastewater. But in general, at least in the academic world, we consider that water of better quality than many of our drinking water coming out from the tap.
Yeah, and I would just add, we don't think about it, but in many locations around the U.S., we are actually drinking recycled wastewater. If you look at where your water's coming from, you're probably downstream of some place. So there probably is a wastewater plant that's discharging into your river, and you're downstream, and the water supply intake is right there. So it's kind of been happening around the country for decades, but in an unplanned fashion, and we don't call it, water reuse, but it's happening. But there are places where it is designed, and it is starting to happen. And there is, I will agree, in places where it is designed, and this, there's announcements in the city, we're going to do this potable reuse or indirect potable reuse project. There is that yuck factor, that psychological factor, and really takes an educational effort on behalf of the water utility in the city to educate the citizens to look at it more as this is a sustainable option. The quality of the water is incredible. If you look at internationally, there's some cities like Singapore is probably one of the most famous examples. They do have something they call New Water, and they're trying to, and it's actually a national security interest because they're trying to become water self-sufficient so they're not dependent on water from Malaysia. So that Malaysia can't cut off their water supply. So they're reusing the wastewater there and for potable reuse. And then other places in Southern California, for example, Orange County, there's a wastewater treatment plant that's treating it to drinking water quality standards. They pump it into some places where it can soak back into the ground, and then it's pulled out kind of downstream from underground. So it's kind of, in some cases there's an environmental buffer there in between where you're pulling it out for drinking water and you're putting it back in. But you're right, it's an educational effort that's needed by cities to make it happen.
Let me just add that. I got asked that question a lot, but since come to Princeton, I learned a different way. The best defense is offense. Think about the electrons you use. Think about the electricity you use. Whether it's from fossil fuels, whether it's from solar, it's electricity, right? And you wouldn't care whether it's right now it's from solar or from fossil. So you would want a more efficient and environmental friendly way to get your water. And water is H2O. Once technology get advanced, it's H2O. It's really nothing else. And think about the carbon. Whether the carbon is from fossil fuel, from CO2, or from biomass, it's the carbon, it's the ethanol you burn. So if you think about that way, that's really H2O. I mean, if we can advance technology environment, we don't really need to defend this water is from sewage or from other ways. Like Jeff said, it's already happening. You just don't need to think about it. We can guarantee you your water is clean, right? So let's change that psychological burden in there. It's not a matter of how clean the water is. It's here, right? So.
Question for Jeff. I noted you said 115 different technologies on your portal. Are you curating those in any way to try, and to what extent are there differences other than size of facility that would be highly germane to, is there kind of one set of technologies that make a lot of sense for most places?
Yeah, that's a good question. Yeah, we do. We are curating them to some degree. We invite technology providers to submit an application to the program, so there's no charge for someone to submit an application. There's 10 questions in there for the technology provider. It's common questions that most end users would want to ask about the technology. You know, what does the technology do? What are the benefits? Has it been piloted or demonstrated anywhere? Who are the people involved? Where is it on the technology readiness level spectrum? Are you down in the lab, or is this something that's maybe newly commercialized but not widely applied? We also ask them, what are they looking for to advance the technology? Are they looking just for end users, or do they need a third-party evaluation or a demonstration? So we get those applications in. We set up a volunteer expert peer review panel to review those applications based on a set of criteria and determine whether or not to accept it into the program. So then once we accept it into the program, we work to shine a spotlight on that and get it in front of utilities, potential end users, for purposes of either adoption, if it's ready for adoption, or for a collaborative pilot or demonstration. So that's, in general, how the program functions. So the technologies that are in there, we don't guarantee. It's more of a screening level that we do at that point. So we don't say the technologies in there are necessarily going to work, but we say these are really promising technologies that need to be looked at or investigated further through a pilot or a demonstration, for example.
One last question. Sorry.
You know, is there any way we can rethink the whole thing of the water differently? The reason is we have a thick oceans. There's more water there in the world. Okay, there's more water there than we could ever use it. But the question is, how do you desalign that? Is there any way we can rethink? How do you invent cost-effective processes to desalign?
Let me respond quickly, because I know we're over time. The U.S. federal government did a report on this last year. It was put out by the White House on the future strategies for addressing sea level rise in cities that are next to the ocean. What they found is that we will actually need to build out significant desalination infrastructure, and that some of the necessary things that we will need to be able to deploy large scale are more renewables, so that we can have cheaper electrons, lower carbon electrons on the grid to actually service the production of fresh water from saline waters. So this is it's a good report. It was by the Office of Science and Technology Policy, and so if you Google Future Water U.S. Science and Technology Policy, you'll probably be able to find it, and it outlines actually, it does answer some of the questions about what our capacity is and how we solve water problems by using seawater.
Those things.
Let's thank our panelists again. Appreciate great discussions, and I'll give to Barry.